This is how it ends in movies. But in reality, civilization doesn't collapse in a single explosion. It collapses slowly, silently, and often without warning. Asteroids are not monsters. They don't hate us. They don't target Earth. They are ancient travelers, older than our planet, moving through space on paths set billions of years ago. Most will never touch us, but a few have already changed the course of life on Earth. Stay with us. This documentary begins now. And if you value serious, long-form science topics like this, consider subscribing. What if I told you that right now, at this very moment, there are thousands of massive rocks hurtling through space at tens of thousands of miles per hour, and any one of them could end civilization as we know it? This isn't the plot of a Hollywood disaster movie. This is reality. February 15th, 2013. Chelyabinsk, Russia. A meteor just 20 meters across explodes over the city with the force of 30 Hiroshima bombs. The shockwave shatters windows across 6 cities. Over 1,500 people are injured. Dashcams capture the blinding flash that turns night into day. And here's the terrifying part. We never saw it coming. This wasn't even a particularly large asteroid. Just a small rock, a cosmic pebble really. But it released more energy than any weapon humanity has ever detonated in war. Now imagine something 100 times larger, 1,000 times larger, 10,000 times larger. They're out there, and they're coming. The question is, will we be ready when the sky falls? To understand what we're facing, we need to go back, way back, 66 million years ago, the late Cretaceous period. Earth is a vastly different world. Dinosaurs have ruled this planet for 165 million years. Tyrannosaurus rex hunts across ancient plains. Triceratops herds migrate with the seasons. Pterosaurs soar through skies that have never known a human eye. It's a warm Tuesday morning, well, if dinosaurs had Tuesdays. In what will one day be called the Yucatan Peninsula, life goes on, as it has for eons. And then, everything ends. An asteroid, 10 kilometers across, that's 6 miles, roughly the size of Mount Everest, has been falling toward Earth for millions of years. It's been traveling through the void of space at 20 kilometers per second. That's 45,000 miles per hour. And now, its journey is over. At 11:47 a.m. local time, the asteroid hits. Let me walk you through what happens in the next few seconds, because the human mind struggles to comprehend destruction on this scale. In the first millisecond, the asteroid is still intact, punching through the atmosphere like it isn't even there. The air in front of it is compressed so violently that it heats to temperatures exceeding the surface of the sun. Within 1 second, the asteroid strikes the shallow sea, covering the Yucatan Peninsula, and penetrates deep into the Earth's crust. The kinetic energy is incomprehensible. 10 billion Hiroshima bombs exploding simultaneously. A fireball, 100 kilometers wide, erupts from the impact site. Everything within 1,000 kilometers is instantly vaporized. The impact excavates a crater 180 kilometers across and 20 kilometers deep in a matter of minutes. But the horror is just beginning. The shockwave races outward at supersonic speeds. In North America, dinosaurs thousands of miles away are killed by the pressure wave alone. Earthquakes, measuring 11 on the Richter scale, a magnitude we don't even have a name for, shake the entire planet. Tsunamis, hundreds of meters tall, scour the coastlines of every continent. Trillions of tons of vaporized rock are hurled into the atmosphere, along with the asteroid itself, now pulverized into cosmic dust. Some of this material escapes Earth's gravity entirely. Much of it comes raining back down, but not as rock, as molten droplets of glass heated to incandescence, turning the entire sky into a broiler. Imagine standing outside and watching the sky itself catch fire. The thermal pulse is so intense that forests across the entire planet spontaneously ignite. Within hours, Earth is wrapped in a blanket of flame. 3/4 of all forests are burning simultaneously. Any creature larger than a bread box that hasn't found shelter is cooked alive. The lucky ones die in the first day. Then comes the darkness. The impact has ejected so much material into the atmosphere that the sun is blocked out. Temperatures plummet. Photosynthesis stops. The base of the food chain collapses. In the oceans, plankton die. On land, plants wither. The herbivores starve. Then the carnivores starve. This impact winter lasts for years. When the dust finally settles, Earth has lost 3/4 of all species. The age of dinosaurs is over. In the aftermath, small mammals emerge from their burrows into a shattered world. They survive. They adapt. They evolve. And 66 million years later, their descendants us look up at the sky and wonder, could it happen again? The answer is yes. Absolutely yes. Let's fast forward to June 30th, 1908. Siberia, a remote forest near the Tunguska River. The indigenous Evenki people are going about their mourning when the sky explodes. A fireball brighter than the sun streaks across the sky. Witnesses 60 kilometers away report feeling heat so intense they think their clothing is on fire. Then comes the blast. An asteroid or comet, estimated at 50 to 60 meters across, detonates in the atmosphere with a force of 15 megatons, roughly 1,000 Hiroshima bombs. The explosion occurs at an altitude of 5 to 10 kilometers, and the shockwave levels 2,000 square kilometers of forest. 80 million trees are flattened, all pointing away from the epicenter like matchsticks. If you could fly over the site, you'd see a butterfly pattern of destruction that's visible from space. Seismographs around the world register the blast. In Western Europe, the night sky is so bright, people can read newspapers at midnight for several days afterward. And here's what keeps scientists awake at night. The Tunguska event occurred over one of the most remote regions on Earth. If the asteroid had arrived just 4 hours later, 4 hours, Earth's rotation would have placed Moscow directly in its path. Instead of flattened trees, we'd be talking about millions of dead. This wasn't 66 million years ago. This was barely more than a century ago. Within living memory of people alive today. Now, let me tell you about some asteroids you probably didn't hear about. 2019. Okay. On July 25th, 2019, an asteroid between 50 and 130 meters across roughly the size of a football field passed within 73,000 kilometers of Earth. That's less than 1/5 of the distance to the Moon. That's closer than many of our satellites. We detected it 24 hours before closest approach. 24 hours. If 2019 OK had hit a major city, it would have caused destruction equivalent to a large nuclear weapon. And we had 1 day's warning. In February 2013, yes, the same month as Chelyabinsk, another asteroid, 2012 DA 14, passed within 28,000 kilometers of Earth. This one we actually knew about in advance, having discovered it a year earlier. But here's the thing. On the very same day, Chelyabinsk happened. 2 completely unrelated asteroids. One we knew about and one we didn't, both making close approaches on the same day. The universe has a dark sense of humor. In 2020, an asteroid the size of an SUV passed within 3,000 kilometers of Earth. That's closer than some satellites. We detected it 6 hours after it had already passed. Between 2000 and 2013, nuclear weapons sensors detected 26 asteroid impacts in Earth's atmosphere, releasing energy between 1 and 600 kilotons. Most exploded over oceans or uninhabited areas. We simply didn't notice. The cosmos is taking shots at us constantly. We've just been lucky, but luck runs out. Let's talk about what's actually out there. Between Mars and Jupiter lies the asteroid belt, a vast ring of rocky debris left over from the formation of our solar system 4.6 billion years ago. There are millions of asteroids in this belt, ranging from tiny pebbles to Ceres, a dwarf planet 940 kilometers across. For the most part, these asteroids stay where they are, kept in check by Jupiter's immense gravity. But sometimes, through collisions, gravitational interactions, or just cosmic bad luck, an asteroid gets nudged onto a new trajectory. One that crosses Earth's orbit. We call these near-Earth objects, or NEOs. As of 2024, we've catalogued over 34,000 NEOs. More than 2,300 of them are classified as potentially hazardous asteroids (PHAs). That designation means they're larger than 140 meters across, and their orbits bring them within 7.5 million kilometers of Earth's orbit. 7.5 million kilometers sounds like a lot, right? It's not. In cosmic terms, that's like a bullet passing millimeters from your head. Now, let's talk about size, because size determines the level of catastrophe. Objects under 25 meters typically burn up in the atmosphere or explode before impact, like Chelyabinsk. These are your city killers if they hit just right, capable of devastating a metropolitan area. Between 25 and 140 meters, you're looking at regional destruction. An asteroid on the small end of this range could wipe out an area the size of a small country. Think Tunguska, but potentially over a populated region. From 140 meters to 1 kilometer, we enter civilization-threatening territory. An impact from an object in this range would cause continental damage, trigger global climate effects, and could collapse modern civilization through cascading failures of our interconnected systems. Above 1 kilometer, you're dealing with potential extinction events. These impacts affect the entire planet. Billions die. The survivors face a world that might not recover for centuries. And above 10 kilometers, well, we've already discussed what happened to the dinosaurs. The good news? We've found most of the really big ones, the dinosaur killers. NASA estimates we've discovered about 95% of near-Earth asteroids larger than 1 kilometer. The bad news? That other 5% is still out there somewhere. And for the medium-sized ones, the 140-meter class, we've only found about 40% of them. There are an estimated 25,000 near-Earth asteroids, larger than 140 meters. We don't know where 15,000 of them are. So why is finding asteroids so difficult? First, they're dark. Most asteroids have a surface albedo that's reflectivity similar to charcoal. They don't glow. They don't broadcast their location. They're just dark rocks tumbling through the darkness of space, visible only because they occasionally block starlight or reflect a tiny fraction of the sun's rays. Second, they're fast. Near-Earth asteroids typically travel at speeds between 10 and 40 kilometers per second relative to Earth. That's 20,000 to 90,000 miles per hour. You can't exactly pull one over for speeding. Third, and this is the real problem, they can come from the direction of the sun. When an asteroid approaches from the sunward side, our telescopes are effectively blind. You can't point a telescope at the sun without damaging it. There's a whole region of space we simply can't monitor during daytime hours. Chelyabinsk came from this blind spot. Currently, our detection network relies primarily on ground-based telescopes. The Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, and the Atlas system scan the night sky systematically, taking images and comparing them to previous nights. If something has moved It might be an asteroid. This sounds simple, but consider the scale of the problem. The sky contains billions of stars. We're looking for tiny, dark objects moving against this background. It's like trying to spot a single charcoal briquette thrown across a football stadium at night. And we're doing this every single night, in all weather, processing millions of data points. The good news is, we're getting better at it. In 1998, NASA was tasked with finding 90% of near-Earth asteroids larger than 1 kilometer. Mission accomplished by 2010, we'd hit that target. In 2005, the goal expanded. Find 90% of NEOs larger than 140 meters by 2020. We're still working on that one. Current estimates put us at about 40% completion, but help is coming. NASA's NEO Surveyor, scheduled to launch in 2027, will be a space-based infrared telescope specifically designed to find asteroids. Unlike ground-based telescopes, it can detect the heat signature of asteroids, making them much easier to spot. And it can observe in directions that ground telescopes can't, including toward the Sun. NEO Surveyor could find the remaining 60% of those 140-meter class asteroids within 5 years of operation. Still, there's a sobering reality. We can only protect ourselves from threats we can see coming. And right now, there are thousands of potential civilization-ending asteroids we haven't found yet. Any one of them could be on a collision course with Earth. We just don't know. Let's talk probabilities, because numbers can be both reassuring and terrifying. A Tunguska-sized impact, an asteroid 50 to 60 meters across, occurs roughly once every 100 to 300 years. We're actually overdue for the next one, statistically speaking. Chelyabinsk-sized events 20 meters happen approximately once every 60 years. Mark your calendars for the 2070 seconds. Now we get into the really bad ones. An asteroid 140 meters across, large enough to cause regional devastation, impacts Earth roughly once every 10,000 to 20,000 years. That sounds like a long time, but remember, human civilization is only about 12,000 years old. We've existed as a species for about 300,000 years. On these timescales, 20,000 years is nothing. A kilometer-sized asteroid capable of threatening modern civilization. Once every 500,000 to 1 million years. The dinosaur killer, 10 kilometers across. Once every 100 to 200 million years. We're safe from that one for a while. But here's the thing about probability. It's not a schedule. The universe doesn't care that Tunguska happened 116 years ago. So we're safe for another couple centuries. Probability doesn't work that way. Think about it like this. If I flip a coin and it comes up heads 10 times in a row, what are the odds the next flip is tails? Still 50-50. The coin doesn't remember. The universe doesn't remember. An asteroid could hit tomorrow, or in 1,000 years, or next Tuesday. And here's another uncomfortable truth. Even a 1 in a million chance, given enough time, becomes a certainty. If something has a 0.001% chance of happening in any given year, over 100,000 years, it's virtually guaranteed to happen. Earth has been around for 4.6 billion years. Life has existed for 3.8 billion years. Complex life for about 600 million years. In that time, there have been at least 5 major mass extinction events, and asteroid impacts played a role in several of them. The geological record is clear. Bombardment is the default state. The calm period we're living in? That's the anomaly. We are living in a cosmic shooting gallery. The rifleman is blind, firing randomly. The good news is, he misses most of the time. The bad news is he only has to hit once. So are there any asteroids we're currently worried about? Let me introduce you to some of the usual suspects. Bennu, a 500-meter asteroid discovered in 1999, has a cumulative 1 in 1,750 chance of impacting Earth between now and the year 2300. That might not sound like much, but in asteroid terms, that's considered uncomfortably high. NASA was so concerned about Bennu that we sent the OSIRIS-REx spacecraft to study it up close and even brought back samples. The mission partly aimed to better understand Bennu's composition and trajectory, because if we ever need to deflect it, we need to know what we're dealing with. Apophis, a 370-meter asteroid, caused quite a stir when it was discovered in 2004. Initial calculations gave it a 2.7% chance of hitting Earth in 2029. 2.7%. That's terrifyingly high. Astronomers around the world focused their telescopes on Apophis, refining its orbit. The good news: we've since ruled out an impact in 2029. In fact, Apophis will pass within 32,000 kilometers of Earth on the 13th of April 2029, close enough to see with the naked eye, but it will miss us. However, that close pass will alter Apophis's orbit. There's a tiny, tiny possibility, currently calculated as essentially zero, but not absolutely zero, that this orbital change could set up a future impact decades later. We'll be watching Apophis very carefully in 2029. Then there's 2023 DW, discovered in February 2023. For a brief, alarming period, it topped the Torino impact hazard scale at level 1, meaning it had a non-zero chance of impact on Valentine's Day, 2046. Subsequent observations have since reduced the risk to essentially zero, but it serves as a reminder. Every time we discover a new asteroid, there's a period of uncertainty while we determine its exact orbit. And this is the key point. The asteroids we know about aren't really the problem. Once we've catalogued an asteroid and calculated its orbit precisely, we can predict its movements decades or even centuries into the future. We know where they'll be. It's the ones we haven't found yet that should worry you. There's an asteroid out there, right now, that might have Earth's name on it. We just haven't spotted it yet. It could be years away from impact, or decades, or it could arrive next month, coming out of the sun's glare with no warning at all, like Chelyabinsk. That's the nightmare scenario that keeps planetary defense experts awake at night. Not the asteroids on our watch lists, but the one we never saw coming. Let me paint you a picture. A scenario, not prophecy, but possibility. It's a Tuesday night at the Catalina Sky Survey in Arizona. Dr. Sarah Chen is reviewing the automated detection reports from the previous night's observations. Most are asteroids we already know about, their predicted positions matching their observed positions perfectly. Just another routine night cataloging cosmic wanderers. Then she sees it. Object 2026 QR7. New designation. Preliminary orbit suggests it's a near-Earth asteroid, about 400 meters across, based on its brightness. She flags it for follow-up observations. Over the next 3 days, telescopes around the world focus on 2026 QR7. Each observation refines our understanding of its orbit, and with each refinement, the calculations become more disturbing. Within a week, the probability of Earth impact has risen from 0.01% to 2%. That's enough to trigger notifications to NASA's Planetary Defense Coordination Office and the International Asteroid Warning Network. Within 2 weeks, it's 15%. Emergency protocols are activated. The world's most powerful telescopes are redirected to observe this single asteroid. 3 weeks after discovery, the probability hits 95%. The uncertainty margin collapses. The orbital calculations are refined to high precision. And the verdict is in. Asteroid 2026, QR7, will impact Earth in 3 years, 2 months, and 17 days. Impact location: the North Atlantic Ocean, approximately 600 kilometers west of Ireland. The first question everyone asks is, "Are you sure?" Yes, we're sure. The orbit is now known to within meters. Multiple independent observations from dozens of facilities confirm it. The margin of error has shrunk to essentially zero. Barring some unpredictable event, another asteroid hitting this one, which is cosmically unlikely, impact is certain. The second question is, can we stop it? We're about to find out. The President of the United States addresses the nation on a Tuesday evening. Other world leaders make simultaneous announcements. The message is carefully coordinated, written by committees, reviewed by scientists, and designed to inform without causing panic. It doesn't work. Within hours, the world changes. Stock markets crash as investors flee to what exactly? Gold? Bitcoin? What currency has value if civilization might end? The global economy enters a seizure as decades of assumptions about the future evaporate. Grocery stores are stripped bare in a matter of days. Not because of the asteroid, it's still 3 years away, but because people panic. Supply chains, already fragile, begin to buckle under the strain. Governments activate emergency response protocols that were written for nuclear war. The United Nations Security Council holds an emergency session. For the first time in human history, the entire world faces a common threat that doesn't care about borders, ideologies, or politics. NASA, ESA, Roscosmos, CNSA, ISRO, every space agency on Earth begin working together on an unprecedented scale. The International Asteroid Defense Coalition is formed within weeks. Resources that would have taken decades to allocate are approved in emergency sessions. But here's the cruel reality. Even working together, even with unlimited budgets, 3 years isn't much time. The plan that emerges is straightforward in concept, but staggeringly complex in execution. A kinetic impactor mission. We're going to hit the asteroid with a spacecraft traveling at high speed, changing its velocity enough to cause it to miss Earth. It worked with DART in 2022 on a small-scale test. Now we need to do it for real, with everything on the line. Multiple missions are planned as backup. Different launch windows, different trajectories, different impact strategies. We're not taking chances. The first mission launches 4 months after discovery. A repurposed heavy-lift rocket carries a hastily constructed impactor spacecraft on a trajectory to intercept 2026 QR7. If everything works perfectly, it will hit the asteroid 2 years before the asteroid would hit Earth, giving the small change in velocity time to accumulate into a large change in position. But spacecraft can fail, rockets can explode, and even if we hit the asteroid, we're not certain of its internal structure. Is it solid rock, a loose rubble pile, solid iron? The answer determines how effective our impact will be. For now, all we can do is watch, wait, and prepare for the worst. Life goes on, but it's different now. Some people quit their jobs. Why work if the world might end? Others throw themselves into their work, seeking normalcy in routine. Birth rates plummet. Marriage rates spike. Everyone's processing the threat differently. Religious movements see a surge in membership. Doomsday cults emerge, claiming special knowledge or salvation. Conspiracy theories flourish. It's not real. It's a government hoax. Or it's real, but they're not telling us something worse. Mental health services are overwhelmed. How do you live normally knowing there's an expiration date hanging over everything? Some people are paralyzed by anxiety. Others experience a strange liberation if it might all end anyway. Why not take that trip, write that novel, tell that person you love them? Months pass. The first deflection attempt fails. A guidance system malfunction causes the impactor to miss the asteroid by 800 kilometers. There are backup missions, but each failure reduces our margin for error. The second attempt, 6 months later, succeeds. Telemetry confirms impact. Telescopes observe the flash as tons of spacecraft slam into ancient rock at 6 kilometers per second. Dust erupts from the impact site, visible from Earth. Now comes the waiting. It will take weeks to determine if the velocity change was sufficient, months to know if we've moved it enough. And when the answer comes, it's devastating. We changed the asteroid's velocity by 3 millimeters per second. We needed 5. The impact will still occur, but the predicted impact point has shifted from the North Atlantic to the coast of Ireland. A third mission is being prepared, but time is running out. Let's say the third mission fails, or never launches, or there's no time. Impact day arrives. Most of Western Europe has been evacuated. Tens of millions of refugees have fled inland and south. Ireland's population has relocated to Britain and France. The coasts of Britain, France, Spain, and Portugal are ghost towns. But you can't evacuate the ocean. You can't evacuate the atmosphere. And you can't evacuate the global ecosystem. At 14:23 Universal Time, asteroid 2026 QR7 enters Earth's atmosphere. For the people watching from safe distances, and billions are watching, it's being live-streamed from dozens of locations. The asteroid appears as a bright point of light that rapidly grows brighter. It crosses the sky in seconds, leaving a trail of ionized air that glows like a wound in the heavens. Impact occurs 200 kilometers west of Cork, Ireland, in the Celtic Sea. The asteroid strikes the ocean at 20 kilometers per second. The water doesn't act like water at these speeds, it acts like concrete. The asteroid transfers all its kinetic energy in a fraction of a second. An explosion with the force of 10,000 megatons, 600,000 Hiroshima bombs, creates a fireball 50 kilometers across. The ocean is vaporized in a hemisphere around the impact point, creating a cavity that briefly exposes the seafloor. Then, the water collapses back and the tsunamis begin. Waves 300 meters high radiate outward at 800 kilometers per hour. Ireland, already evacuated, is scoured clean. The waves hit the British coast 20 minutes after impact. France, Spain, Portugal, every coastline facing the Celtic Sea is inundated. The eastern seaboard of North America has 4 hours warning. Most people have evacuated, but 4 hours isn't enough to move entire populations. New York, Boston, and every coastal city experiences tsunamis 50 to 100 meters high. The shockwave rattles windows across Europe. Earthquakes register magnitude 8. The impact crater on the ocean floor is 15 kilometers across, but the immediate destruction is just the beginning. The impact has ejected billions of tons of water and vaporized rock into the atmosphere. Within hours, the ash begins to spread, blocking sunlight. Temperatures start to drop. Agriculture across Europe and North America faces catastrophic failure. And this is what a 400-meter asteroid does. Not an extinction event, not a dinosaur killer, just 400 meters of rock. Civilization doesn't end, but it's fundamentally changed. Hundreds of millions dead. Billions affected by crop failures and climate disruption. The global economy shattered, all because we didn't see it coming in time. That was a scenario, a possibility. But here's the reality. We don't have to let it happen. For the first time in human history, we have the technology to see these threats coming and the capability to do something about it. We are the first generation that doesn't have to just accept cosmic bombardment as an inevitable force of nature. Let me tell you about what we can actually do right now, today. if we discovered a threatening asteroid. The toolbox of planetary defense is limited but growing. And unlike most existential threats, humanity faces climate change, pandemics, nuclear war. Asteroid impacts are completely preventable, with enough warning time. The key phrase there is enough warning time. September 26, 2022. A date that should be as famous as the moon landing, but most people have never heard of it. On that day, a NASA spacecraft called DART, the Double Asteroid Redirection Test, deliberately crashed into an asteroid named Dimorphos at 6.6 kilometers per second. This wasn't a drill. This was the real thing. The first time in history that humanity intentionally altered the orbit of a celestial body. Dimorphos is a small moon orbiting a larger asteroid called Didymos. It's about 160 meters across, roughly the size of the Great Pyramid of Giza. And it was perfect for testing planetary defense, because it wasn't threatening Earth. We could hit it without any risk. DART was essentially a refrigerator-sized battering ram, equipped with cameras and autonomous navigation. It had one job: hit the asteroid. The collision was observed by telescopes around the world, and up close by a small Italian satellite that separated from DART before impact. The images are stunning. You can watch them on YouTube. You see Dimorphos growing larger and larger in the camera view, its surface resolving into boulders and craters, and then impact. The results exceeded expectations. The collision changed Dimorphos's orbital period around Didymos by 33 minutes, far more than the minimum 73 seconds needed to declare the mission a success. We moved an asteroid. Humanity pushed a mountain through space, using nothing but kinetic energy. The principle is simple. Momentum is conserved. When you hit something, you transfer momentum. The spacecraft has mass and velocity, and that momentum gets transferred to the asteroid. The asteroid speeds up or slows down depending on where you hit it, and its orbit changes. This works best with years or decades of warning. A tiny change in velocity, given enough time, results in a huge change in position. If we altered an asteroid's velocity by just 1 centimeter per second, 10 years before it would have hit Earth, that translates to a positional change of 3 million kilometers by the time it reaches Earth's orbit. Remember, Earth is only 12,000 kilometers across. We don't need to move an asteroid far, we just need it to miss. The kinetic impactor approach is our current, proven technology. If we found a threatening asteroid today and had 10 or more years of warning, we could handle it with our existing capabilities. It would be expensive, challenging, and nerve-wracking, but it's doable. But what if we don't have 10 years? What if we only have 5? There's another approach that sounds like science fiction, but is entirely real. The gravity tractor. Here's the concept. Instead of hitting the asteroid, you park a spacecraft next to it, just hovering there, station-keeping with ion thrusters or other propulsion. The spacecraft and the asteroid, being massive objects, exert gravitational attraction on each other. Now, the spacecraft is tiny compared to the asteroid, so its gravitational pull is minuscule. But if you leave it there for years, that tiny, constant tug accumulates. The asteroid's orbit gradually changes. Think of it like trying to redirect a train. You can't push it all at once, but if you pulled with the force of a strong person for hours, days, months eventually, you'd change its course. The advantage of a gravity tractor is precision. You're not hitting the asteroid and hoping for the best. You're applying a controlled, constant force. You can steer it exactly where you want it to go. The disadvantage is time. This approach requires decades of warning. If we only have 5 or 10 years, a gravity tractor won't cut it. There's also a practical problem. Keeping a spacecraft in position next to an asteroid for years requires propellant. A lot of propellant. The mass of the propellant becomes a significant fraction of the mission mass, which makes launches expensive. Still, for asteroids we discover early decades before potential impact, a gravity tractor might be the safest, most controlled method of deflection. Now let's talk about the method Hollywood loves: nuclear weapons. First, let me dispel the myth. We would not blow up an asteroid with a nuclear bomb. That's a terrible idea. If you fracture a single large asteroid into dozens or hundreds of smaller pieces, you haven't solved the problem, you've made it worse. Now, instead of one impact, you have a shotgun blast of impacts spread across a wider area. But nuclear weapons do have a role in planetary defense, just not the way movies depict it. The concept is called a nuclear standoff burst. You detonate a nuclear weapon near the asteroid, not on it. The explosion vaporizes a layer of material on the asteroid's surface. That vaporized rock expands rapidly, acting like a rocket engine and pushing the asteroid in the opposite direction. This approach has serious advantages. Nuclear weapons release tremendous energy, far more than any kinetic impactor we could build. A nuclear standoff burst could change an asteroid's velocity by meters per second, not centimeters per second. That's orders of magnitude more effective. This is our emergency option. If we only have a year or two of warning and the asteroid is large, a nuclear deflection might be our only choice. There are, of course, complications. First, there's politics. The Outer Space Treaty of 1967 prohibits placing nuclear weapons in space. Now, this treaty was written during the Cold War to prevent nuclear weapons being stationed in orbit, not to prevent planetary defense. There are provisions for exceptions in cases of global emergency, but the legal and diplomatic framework would need to be worked out in advance, ideally before we're facing an actual impact. Second, there's uncertainty about effectiveness. We've never tested a nuclear deflection. We don't know exactly how different types of asteroids would respond. A solid rock might respond differently than a loose rubble pile. We'd be making educated guesses under extreme time pressure. Third, there's the risk of unintended consequences. What if the deflection works, but we miscalculate and deflect it into a trajectory that causes an impact a few orbits later? We need to be very, very sure of our calculations. But despite these challenges, nuclear deflection remains in our planetary defense toolkit, because if the alternative is certain impact, we'll use every option available. Here's the brutal truth about planetary defense. It's all about early warning. With 20 years of warning, deflecting an asteroid is relatively straightforward. Multiple kinetic impactor missions, careful trajectory planning, ample time for course corrections. We could handle it with existing technology. With 10 years of warning, it becomes challenging, but still manageable. We'd need to execute flawlessly, with minimal room for error. With 5 years, we're in difficult territory. Nuclear options might be necessary. There's little time for backup plans. With 1 year or less, our options become extremely limited. For smaller asteroids, evacuation might be our only realistic response. For larger ones, well, we'd better hope we never face that scenario. This is why detection is so critical. The earlier we see the threat, the easier it is to handle. Every additional year of warning exponentially increases our chances of success. Right now, our detection network could spot a dinosaur killer years or decades in advance. That's good. But a 300-meter asteroid approaching from the sun's direction? We might get weeks of warning. Or days. Or hours, like Chelyabinsk. We need better detection. We need space-based telescopes that can see the entire sky, including toward the sun. We need international cooperation and data sharing. Because the difference between success and catastrophe is measured in time. Let's zoom out for a moment and look at the big picture. Humanity faces numerous existential risks: climate change, nuclear war, pandemics, artificial intelligence, biotechnology. Each of these threats has something in common. They're created by us. They're the result of human activity. Asteroid impacts are different. They're entirely natural. They've been happening since Earth formed 4.6 billion years ago. They'll continue happening long after we're gone. But here's what makes asteroid defense special among all existential risks. It's completely solvable. We can't stop climate change overnight. It requires decades of coordinated effort and fundamental changes to our energy systems. We can't eliminate nuclear weapons. Thousands exist, and the knowledge to build them is permanent. We can't guarantee a pandemic won't emerge. Nature is endlessly creative at producing novel pathogens. But asteroids, with sufficient investment in detection and deflection capabilities, we can effectively eliminate this threat. Not reduce it, not manage it, eliminate it. Asteroid impacts are predictable with the right technology. They're detectable years or decades in advance, and they're preventable with engineering we already understand. This is unique. How often do we face an existential threat that's actually solvable? And yet, our investment in planetary defense is minuscule. NASA's Planetary Defense Coordination Office operates on roughly $150 million per year. The entire global investment in asteroid detection and deflection is probably less than $500 million annually. Let me put that in perspective. That's less than the cost of a single military fighter jet. That's less than the budget for most Hollywood blockbusters. That's less than what humanity spends on potato chips in a month. We're talking about protecting the entire planet, all of civilization, every person alive and yet to be born, for less than what we spend on snack food. If we wanted to build a comprehensive planetary defense system, a network of space-based telescopes to detect every threatening asteroid, a fleet of deflection spacecraft on standby, international coordination, and rapid response capabilities, it would cost somewhere between $5 and $10 billion globally over the next decade. $10 billion. That's less than the cost of a single aircraft carrier. It's a rounding error in most national budgets. It's less than $1 per person on Earth per year. For that investment, we could essentially guarantee that no asteroid larger than 50 meters reaches Earth without decades of advance warning. That's the most cost-effective insurance policy in human history. But there's another layer to this story. Planetary defense isn't just about protecting Earth today. It's about the long-term survival of our species. Here's an uncomfortable reality. As long as all of humanity lives on one planet, we're vulnerable. Not just to asteroids, but to any global catastrophe. A supervolcano eruption, a gamma-ray burst from a nearby supernova, a cascading ecological collapse. The dinosaurs ruled Earth for 165 million years. They were successful beyond measure, but they made one critical mistake. They kept all their eggs in one basket. When the asteroid struck, they had nowhere else to go. We have the opportunity to do better. Becoming a multi-planetary species provides the ultimate insurance policy. If we establish self-sustaining colonies on Mars, orbital habitats, or outposts throughout the solar system, then no single event, no matter how catastrophic, can end humanity. An asteroid could devastate Earth, but human civilization would survive on Mars. A plague on Mars would leave Earth untouched. We become resilient not through armor, but through redundancy. This isn't science fiction. We have the technology to begin this process now. SpaceX is developing Starship specifically to make Mars colonization possible. NASA's Artemis program aims to establish a permanent human presence on the Moon. China, India, and other nations have their own ambitious space programs. The same technologies we're developing for planetary defense, powerful rockets, deep space navigation, asteroid resource utilization. These are the same technologies we need to become a spacefaring civilization. In a sense, the threat of asteroid impacts is pushing us to develop capabilities that will ensure our long-term survival in ways we haven't even fully imagined yet. Here's a dark thought to consider. The Fermi paradox asks, if intelligent life is common in the universe, where is everyone? Why haven't we detected any signs of other civilizations? There are many proposed answers, but one is particularly relevant to our discussion: the Great Filter. The idea is that there are barriers or challenges that prevent civilizations from reaching advanced stages of development. These filters might be behind us: the emergence of life, the evolution of intelligence, the development of technology, or they might be ahead of us. Could asteroid impacts be one of these filters? Think about it. Every planet in every solar system is subject to cosmic bombardment. It's universal, and the window of vulnerability is specific. A civilization must be advanced enough to detect and deflect asteroids, but that capability must be developed before a catastrophic impact occurs. Earth has been lucky. We've had 10,000 years of civilization without a major impact. That gave us time to develop science, technology, spaceflight, all the tools we need to protect ourselves. But another civilization might not be so fortunate. They might reach our current level of technology only to be wiped out by an impact before they could develop planetary defense. Or worse, they might develop the capability to detect asteroids, but not deflect them. Imagine knowing with certainty that your civilization will end in 20 years and being powerless to stop it. That's a special kind of horror. If asteroid impacts have prevented other civilizations from surviving long enough to become spacefaring, then our success in developing planetary defense isn't just about protecting Earth. It's about proving that intelligent life can survive this particular cosmic challenge. We might be one of the first civilizations in our galaxy to pass this test. That's worth thinking about. So, where does that leave us? Let's return to the question I asked at the beginning. Will we be ready when the sky falls? The answer is, we're getting there. But we're not there yet. We've proven we can detect most large asteroids. We've proven we can hit an asteroid and change its orbit. We have the basic tools we need. What we lack is comprehensive coverage. We need better detection of medium-sized asteroids. We need space-based telescopes to cover blind spots. We need international agreements on rapid response. We need deflection capabilities that can be deployed on short notice. All of this is achievable with technology we have today. It's not a question of can we do it, but will we do it? And that's ultimately up to us, up to humanity, up to whether we decide this threat is worth taking seriously. Because here's the thing, asteroid impacts aren't a matter of if, they're a matter of when. The universe doesn't care about our politics, our economies, our daily concerns. It operates on timescales where 1 million years is nothing. And in those vast timescales, impacts are inevitable. But for the first time in the 4.6 billion year history of Earth, there's a species on this planet with the capability to look up, see the threat coming, and do something about it. We are that species. This is our moment. Our ancestors lived at the mercy of nature, floods, earthquakes, storms, and yes, impacts from space. They had no choice but to endure whatever the cosmos threw at them. We have a choice. We can invest in detection systems. We can develop deflection technologies. We can coordinate internationally. We can decide that protecting our planet, our civilization, our future is worth the cost of a few fighter jets. Or we can wait. We can assume it won't happen in our lifetime. We can kick the responsibility to future generations. But those future generations might not have time to prepare. They might be the ones looking up at a bright point of light growing in the sky, knowing they're out of time. So I'll ask you one final time. Will we be ready when the sky falls? The answer depends on what we do right now, today, in this moment, when we still have time. Because somewhere out there, in the darkness between worlds, there's an asteroid. It might be years away from Earth, or decades, or centuries. But it's coming. The question isn't whether it will arrive. The question is whether we'll be waiting for it. Look up at the night sky tonight. Those points of light have been watching over Earth for billions of years. They've seen impacts beyond counting. They've seen species rise and fall. Now they're watching us, the first species that might actually survive what's coming. Let's not disappoint them.